the planetarium show, and if the weather is good, which it hasn't been. It's good today, but when we had the observatory available, it wasn't. But if the weather's good on Saturdays, we have our observatory open, and you are welcome to come and look through the telescope and enjoy looking at the wonders of the universe.
The wonders of the universe.
Yes, indeed.
Yeah, I did. That was very good. I watched the transit of Venus here, where transits went across the sun. You could actually see the shadow of Venus, and we watched it here. It was really cool. It only happens once every 100 years, I think, or something like that.
It does that.
So it was. You can. The planetarium is a really nice place. So we're ready to go. Good morning, everyone. My name is Bill Waberson. I'm a nuclear engineer. I work at Savannah Riverside. I graduated from the University of Florida, if you notice my shirt. We're going to take a journey to the center of the atom. Did you guys know, you guys are all on this side of the classroom, and so I'll have to stand over here. Does anybody know what's the center of the atom? This is where you talk. The nucleus, does everyone agree with that? The nucleus? That's right, so we're going to focus on the nucleus. And the nucleus is made up of protons and neutrons, so we're going to talk about that. This presentation is provided by Citizens for Nuclear Technology Awareness here in Aiken, ANS, which has a presence here in Aiken and Augusta, and I helped design this, so my name's on there as well. We're going to start, you guys should know this, so it's a review, just to get everybody on the same page. We're going to review the makeup of an atom. So there are two parts of the atom. We have a nucleus and an electron cloud. The nucleus is in the center, and the electron cloud is around the outside. What parts are in the nucleus? You guys should know this, or you can read it. What parts are in the nucleus? This is a participation class, so you guys have to start participating. We're going to actually do a lot of hands-on stuff, so you're going to start, your voices are important, so let's talk. Protons and neutrons. So let's just say protons and neutrons. Red and blue. Red are protons, blue are neutrons. That's how color they really are. No, we can't. They don't have a color. So if I took two protons and I tried to put them together, would they stick together? Why? Say it louder. Why aren't they attracted to each other? They have the same charge, so like things repel, right? Opposites attract. These are not opposite. Now a neutron is neutral. So a neutron, can it stick to a proton? It can. They're not opposite, but they don't push apart. So neutron acts like the glue that holds an atom together. You can put one proton to a neutron, then you take another proton and stick it to a neutron. And that's how atoms are assembled. Does that make sense? So when we look at our protons and our neutrons, the proton has a charge of 1, neutron has no charge. A proton has a mass of a 1 atomic mass unit. That's just the size of 1. The neutron is the same size. An electron has a charge of -1, the opposite of a proton, and its mass is 1/1800th the size of a proton or neutron. It's tiny, really tiny. If we drew it to scale on here, you wouldn't even see it. It's very, very tiny. And so the mass of an atom is made up mainly by protons and neutrons, almost all of it. Any questions on that? What is this? Periodic table. This side of the class is talking. Let's get all of us. You guys know this periodic table. It has a funny shape. Do you know why it has a funny shape? It's because it's laid out by the number of electrons, how many electrons it have. So it's all laid out by its electrons. This piece down here actually fits in here. And so the table is really wide, and the problem is it doesn't fit well on a page. So they actually cut it out and put it down below. It's called the lanthanides and actinides. But this is all laid out by electrons. Now this is for chemists, because electrons are how chemistry works. And nuclear people like me, we don't really care about electrons. Electrons do whatever the protons do. The protons drive everything in the atom. And so this has 1 proton, 2 protons, and the electrons match. And so when you go to your other class, they're going to talk about electrons. And you can remember to tell them, that neutrons and protons are what really matter. Electrons don't matter. When you go to your next class, tell them that and see how they react. You're going to learn about electrons there. But so this periodic table is set up like this. But in reality, this hydrogen, I think there are 6 or 7 isotopes of hydrogen. There are more than one kind of hydrogen. There are 40 kinds of mercury. So that if you thought of these as Scrabble tiles, they stack up on top of each other. So you can't see that here, but we're going to demonstrate that in a minute. I mentioned the term isotope. Does anyone know what an isotope is? Anybody? You guys learned this, I think, back in elementary school. So I know you learned it in 3rd grade or 5th grade, but I know it's been a long time. An isotope is the same number of protons, but a different number of neutrons. It has a different mass. So here are 3 isotopes of hydrogen. If you notice, how many protons are in this hydrogen 1? How many? 1. And how many electrons? 1. How many protons in this one?
1.
And how many electrons?
1.
Same here, right? So what happens is, chemically it acts the same. It acts like hydrogen. But you could take and add a little bit of glue to it, and it becomes hydrogen 2. Add a little more glue, it becomes hydrogen 3. If you add more of hydrogen 4, 5, 6, when you get too much or too little glue in an atom, it becomes radioactive. Hydrogen 3 is radioactive. The atom wants to change to a more stable, to get a proper balance of the glue in there. When you have too much glue or too little glue on something, say you had 2 blocks of wood about this big, and you didn't put enough glue between them, what would happen? They'd break apart. What if you had 6 inches of glue between them? What would happen? The glue would break itself, right? The glue wouldn't hold. And so that's how it is in atoms. If you have too much or too little neutrons, the atom breaks apart. Does that make sense? All right, we're almost done with the lecture, and then the presentation. Then we're going to get on to the hands-on part. This is the periodic table related to isotopes. You can see most hydrogen, it's hydrogen 1, a little bit of hydrogen 2. You see down here mercury, they got all kinds of isotopes. And so you'll see that here in a moment yourself. This is a different way to look at the periodic table. Now, this is the last thing we're going to do, and then we're going to get up and start doing some hands-on things. This is the standard nuclear notation. And this is the layout. This is for carbon-12. This is the chemical symbol. You can see how it's C down here for carbon. This is the atomic number, which is the number of protons. And this is the atomic mass, which is the protons plus the neutrons. Remember, the electrons are so small they don't really count. So this is the number of protons and neutrons. So you can see this one has 6 protons. It's the symbol carbon. How many neutrons are in it? No, it's protons plus neutrons, so you have to do subtraction. It's 6 because there's subtraction. You subtract one from the other. Nope. So you're right here. A is equal to Z, which is the number of protons plus the number of neutrons. And so what happens is you have to be able to do that math to do the hands-on thing we're getting ready to do. It's just subtraction, but you have to be able to do it. Now what you'll see is here, carbon-12, carbon-13, carbon-14. The 6 is common for all of them, so sometimes we actually drop the 6 because it's redundant with the term C. Okay, now we're going to practice. How many protons, and everyone has to speak on this, how many protons are in one hydrogen 1? How many protons? 1. Does everyone agree? 1. I agree. 1. How many neutrons are in 3 lithium 7? I want to hear voices over here. 4. I agree. 4. How many protons are in 8 oxygen 17? I heard 9. It's 9. I heard your 9, but I want to hear over here too. It's 9. It's 8. That's actually a typo. I'll fix that for the next lecture. That's typo. It actually is 9. How many neutrons are in one hydrogen 1? I didn't hear any voices. Not 1. 0. You did the subtraction. It was a trick, right? All right. Now we're going to build a 3D periodic table. So everyone get up and come on over here. Be careful of this. I don't want anybody to trip over it. So just make sure nobody steps on that and trips over it. Everybody gather around this side of the table. I'll stand on this side. Everyone get on that side. I'll stand on this side. So there's plenty. There's a typo on that presentation. We'll fix it at the break. All right. So grab one of these tiles and pass them around. And there are 14 of you, and there are 22 of these, so a couple of you grab 2. Just a couple people. This is the Pirac table, and it's a different form of the Pirac table. When everybody has a tile, let me know. If they're extra, pass them around so people get 2. Now, there are some blanks on here. There are some that aren't blank. And this number below is the number of isotopes that they have. And we're going to describe that here in a minute. We talked about isotopes. So we need to fill in the blank spots. Also, if you have mercury, mercury goes here, copernicium goes here, and uranium goes here. But any of the other ones you have to fill in yourself. And this is hydrogen, helium. They number 1, 2, 3, 4. So let's go ahead and start putting them on. Very good. Got potassium right away. Hydrogen. Yeah, we got it. That's good. Perfect. That's it. All right. We're getting close. They number. The 12, so 13 would be right by 14 there. Very good. First 19. We're missing just a couple. We're missing beryllium, and we're missing, what's after sodium? I can't remember. Magnesium. Beryllium is right here. Looks like we're missing boron, right? All right, very good. So uranium goes right here. So go back around to that side table, and I'll show you some things. This is actually, or filled that in. This is actually, if you notice, these numbers are like, 1.01, 6.94. It's not a whole number. And there are really whole numbers of electrons and protons, because these are the averages. For mercury, this is mercury. This is how many isotopes, if we had all of the isotopes stacked up for mercury underneath it. Remember I told you they stack up like Scrabble tiles underneath? This is for uranium. This is copernicium. Now what happens is there are different colors here. The green ones are stable, naturally occurring. The blue ones are radioactive with a long half-life. Many of them are naturally occurring. And the red ones have less than a second they live and they're gone. And so those are very unstable. And so you can see there's a symmetry. Can you see in the green to blue to red? This one, uranium, has no stable. They're all radioactive. Same with copernicium. So that's when we, yes, you had a question?
So why exactly are they spaced out where it goes from red to blue, then green, then another blue?
I'll show you that in a minute. It's good questions. Keep thinking. It's very good. So what now you're going to have to do is all of the rest of these tiles are over there on that table. See that table in the center? And we're going to sort them and stack them underneath. So remember the tiles that you had, but first come over here. Remember what element you had. What we're going to do is take all of these, and we need to sort them by element. And you can see I have the element number is the mass number at the bottom. This sulfur is 16, but you can see here 1, 2, 3, 4, 5, 6, all the way to 19. So go and grab some tiles, and everybody, let's start sorting them, and we'll get them all sorted into their elements, and then we'll place them on the stacks over there.
You're sorting by atomic number?
By atomic number. Mm-hmm.
Okay, which is a very good way to sort.
Yeah, that's how the periodic table does it.
That's one of the basic trends.
That's right. So good. The numbers are on the outside, so what do you got? Mm-hmm. So you got 16, so that would go over where 16 is. See and then just keep doing them. Set them all down on the tables.
Now these all represent isotopes?
These are all isotopes.
Particular elements?
Of everything from hydrogen to potassium.
Oh, the first 19? Mm-hmm. Interesting. Do they all have isotopes?
Yeah.
Oh, they do?
Every one.
And beyond 19?
It gets bigger, all the way to
More isotopes yet?
Mercury is the most, has 40, and then it goes back down. So
Interesting.
So you'll see that in a moment. There we go. That's it. That's right. Not 37, it's all the lower number. Your 16s will all go in pile 16. See 16 over there? Excuse me. That's right.
That's the one point of contention, whether There's so many different places.
That's right. And this
Top
is a
right-hand corner,
nuclear
top left-hand
notation. I think chemistry does it differently sometimes. So, but there is a standard nuclear notation.
Interesting. That's probably and just position on the position on each of the individual ones, so it's in a specific place for the nuclear.
That's right.
Interesting.
That's right.
Interesting.
And so, and there you'll see there's a book that we go by, and so we'll talk about that in a moment. So they're going to stack them up, but once they get them sorted, they will go back to their number that they placed, and then they'll stack them.
Now, who makes those? Who makes those?
I made them.
You made them. You made those squares yourself?
I put
With
my
what
wife.
time? Whether you're still working?
It was Christmas vacation.
You serious?
Yeah.
So you just would use plywood or something?
No, it's plastic. I had a company cut the plastic for me.
You pre-cut it for you? Nice. That was the hardest part, getting them all cut in the squares.
The-
And then, how did you do it? You paint them?
No, it's labeled. They're all got a sticker on them.
Oh, you just use all stickers?
Yeah, you can look.
So but you paint them first.
No, it's a red plastic, and
So you went for red plastic, blue plastic, and how did you find this kind of stuff?
I just had to figure it out.
You just went online looking for.
I know locally. There's a plastic vendor over in Beach Island that I went through.
Interesting. Can I get that name?
Yeah,
So
well,
I'd like to do this myself.
yeah. There's we have all the stuff. I can share it with you when we're done.
Thank you so much.
You're welcome. All right, once they're sorted, remember the tiles that you placed. Go there, and I want you to stack them in numerical order with the lowest number on the top. The lowest number on the top. And then when you're done, I want you to stack them under the white tile over here, just like you see these ones that are examples. You can help if someone seems lost, so you can help. Just stack them numerically once you're there. And if you had two, if you're done first, you can help someone else who had two. So come on over here. Once yours is done, you got them stacked numerically? Come over here. What do you have? Beryllium. So stack them under the white tile and put the white tile on top. And then go grab another stack if someone else needs help. And do one or more. Very good. Stack them under the white tile for which one you have. So once you have your stack, go ahead and bring them over and put them under. You're very good, very good. Looks like you have neon. And just put them right under the neon one. It'll get tricky. The last people putting them in have the hardest time. So try to get them up as straight as you can.
What do we do with the neutron?
Where's the neutron? I'll keep that. I was waiting for someone to find it. Looks like someone left a boron. Are you working boron? Or? Who has boron? There's an extra boron one. That's 17. Put it under there. What you got? Aluminum? Whoop, whoop. You're going to have to help take them up. I know it happens. We have to be careful. It gets tricky the last couple trying to get theirs pushed in. So if you set yours, set them up as straight as they can be so that others can get theirs in. Sometimes.
There we go. There's a missing number.
Yeah, I didn't.
Sometimes they're missing. Sometimes they don't have them. Nature doesn't have every number covered, so sometimes there are some gaps. Here, it's easier if you take that one out and slide them in. And then the white one on top. Yeah, go ahead and put the white one on top. Are we close? The last two are going to be the hardest because they're a hard spot to slide into, huh? Here, we can slide these all down maybe and they give a little more room to get in there. How's that? That's all right. It's okay. Originally on the color, so all right, we'll slide it back in. It's easier if we move the argon over a little bit so you can get those in. All right, you can see how they're very good job, everybody. You can see how there are the different colors. Can everybody see? You can see the different colors and how many isotopes there are. So when you look at the periodic table, you can't really imagine that there's so many things underneath that hydrogen, so many things under that aluminum. And so this is, the nuclear people, we care more about the isotopes, the number of protons and neutrons. So this chart's not very helpful, is it? If I wanted to look at this magnesium, it's underneath and I can't see it. So we use a different chart. It's called the chart of the nuclides. So let me show you how that works. I'm going to take a couple of these. I'm going to show you how it works. So I got some samples. Let's go over this chart over here. Everyone gather around on that side. Now this chart is called the chart of the nuclides. This is what nuclear engineers use. We don't use the periodic table because it's not very helpful. Now the y-axis up this side is the number of protons, which also matches the name of the element, right? Along the bottom are the number of neutrons. And so we're going to spread these out as a matrix. So I have here 1 hydrogen 1. And so how many protons does it have? 1. How many neutrons does it have? 1. No. 0. So we put it at the position of 1 proton, slide it over there, and 0 neutrons. I have a neutron here, which actually does exist by itself for not very long. It's radioactive, that's why it's blue. How many protons are there? You can look on there and see it's 0, right? How many neutrons? 1, so put it in the 0, 1 position. Now I have here aluminum 38. How many protons does it have? 13. How many neutrons does it have? 25. So we come over here to 13. We come over here down the line of 13 till we get to 25. Am I on 13? And so we put it there, 25. So now you guys, the elements that you put together, let's go ahead and transfer them all over here. Leave the white ones on that chart, but put the colored ones over here. See how it makes sense? And leave the uranium and the copernicium and the mercury because they're glued together. Don't try to break those apart. All right, go ahead and start setting them on. You'll find out if you organize them well, they should lay out there really easily. And so you just gotta start laying them out. See the person in green is laying them down improperly because she's going just by the number, but let them figure it out themselves if you ever do it. They'll figure it out themselves. Same up here. It's off the chart. They don't go off the table because you're not doing the math. Remember, it's not the other number. You have to do the subtraction. Once you figure out one, the rest will all lay out right after it. So you just have to figure out one of them. Yeah, it's because he was running off the table. So yeah, that's right. It's all right. Let him figure it out. They're good. It's good. Yeah, let them figure it out. They got it. Yeah. Yeah, neon's in the wrong that one's, yeah.
Yep.
Let me mention something that happened on Friday. One of the tiles was missing.
Was it?
Argon 48, which was clearly not there. But we had the right number of tiles.
But sometimes some are missing.
Not that one.
Is it?
Right in the middle of the tile.
Oh, was it? Did you find it?
No, because we had the right number of tiles. But that one was missing, so I think there's an extra one of another one. Is that possible?
And then the other kits?
I'm not sure.
Yeah. Is it in this one here? This the same kit you used Friday?
No, this kit was okay.
Which one?
What we did is we went and got the tile that was missing out of the other kit, so it's now short one.
I have some spare stickers at home,
Okay.
if you know which one it is.
It was, yeah, argon.
We'll get the other kit today late, and we'll lay it out.
Take a look.
Yeah. How's it going? How's it going? You're close. You're close. You'll start to see some patterns here. They should help you do it. You're starting to see the patterns. It's good that you're helping each other because I see you've kind of corrected some errors. It's good that you're helping each other. Let's keep going. We're almost there. Let's help the sulfur. Let's get a couple started, and then you'll see there's a pattern how they count up. So they don't slide easy, so it'd be easier to pick them up. And so that there's a pattern the way the numbers go. There you go, right there. That's where it goes. And then the rest should count up and just go straight down the line. Maybe not on the old one. I used the other version. That's what the blue book. That's
Where argon 48 is, it doesn't make sense that that one's missing.
okay.
So I'm putting that, this all 14 was next to 16, so I'm trading 14 to 16.
No, it does. I think. It is. It is right. It's this different chart nuclides. I have version 16, not 17. So it's supposed to be missing. You couldn't have gotten one out of the other one then.
No, they took it out of this. Well, that's true. Yeah, obviously. I didn't.
There might not be a 21, some of them don't have all the numbers.
Let's finish our sodiums. We're close. We're missing sodium. Also, you'll notice that this isn't right. We'll see some patterns because you can see they count up 43, 44, 45, 46, 47, 48. This one 45, 46, 47, 49, 49. So it actually needs to slide over right there. And so
21. So you gotta go all the way down to 21. Go up.
that's the way you help.
21's right here.
No, it goes over there, right above your hand. You can see right where your hand is, that's where it goes.
Right here.
Uh-huh.
32 goes
So you do the math. 32.
Minus
right
11
here.
is 21.
It's 32, so it is. Yeah, that's where it is. It goes in that hole right there. That's right. You're right. That's the way you do it. You got to do the math. And that's why we practiced earlier, remember?
32.
That's right. She has some, she needs to get those in the middle too, so that's it, that's it. 22 goes in the hole over there. We're close.
That's 30.
How are we doing? All right, the puzzle is complete. Very good, everyone. Let's look. What patterns do you see? Now, you guys tell me what patterns you see.
It's going up.
They count up this way, right? Which makes sense. They count this way as well, right? How about color-wise?
They match
is the green are kind of in a line, right? And then that's, in nuclear science, we call that the line of stability, because the green are the stable ones. So the stable ones form a balance, they're almost balanced between the neutrons and protons. Remember we talked about the amount of glue? It has to be somewhat balanced. And as it comes up, you'll see it comes up a line. On either side of it, what color do you get? You get the long-lived radioactive, they're almost stable. And then the further away you get from it, what happens? What color is red? What does it mean? Unstable. They become very unstable. And so this is what we use, and we can see all of them. Now this is just a representation of it. Let's show you the, Teresa, can you help me a second? This is the whole chart right here. Now what happens is it's so big that even this is broken up into pieces. It's one big slash. You can see it's broken into 3 pieces. It starts over by Teresa at the where the Z is over there, right up, and it comes up, and where this line is, it starts. Thank you. Starts here, and the gray ones are the stable ones. See the gray ones? And so this is the number of neutrons, this number of protons. It comes up, but there wasn't a big enough piece of paper, so it continues on here, and then it continues on here. And so you guys only went to potassium, which is here down. If we did this whole thing, we'd probably need a gymnasium floor to fill all of it. It would take us all day to fill it in. So you can see there are lots of isotopes. And this is what we use as nuclear engineers. It's called the chart of nuclides on a wall. It's pretty small writing, isn't it? And so we put this on our wall. It kind of brags, I'm a nuclear engineer. What we really use is a book. And here's the book, Chart of Nuclides. And it's broken up into about 100 pieces where we can read it. You can see that? And so we can learn all kinds of properties about each isotope. And that's how it's. And so what we're going to do now is we need to break up into 4 teams. Break up into 4 teams. There are 14 of you, I think. So that'll be 3 per team plus a couple with 4. So break up into teams of 3 or 4. And I'm going to give you each an element. Let's see. 3 or 4. So we want this team to have hydrogen 3. This team is going to have boron 10. This team is going to have carbon 14. And this team will have oxygen 16. Now before we leave, I want to describe one more thing about the periodic the chart of nuclides. What you'll see is the line of stability is naturally occurring phenomena. And so what we do as nuclear engineers, we look for things like carbon-14. Has anybody heard of carbon-14 before? What do they use it for? They use it for archaeological dating to find out there's carbon-14 in the atmosphere, and what they do is they can determine old bones and things up to 60,000 years old by how much radioactive carbon-14 is in it, because it decays. So they use that naturally. If you go to GRU, it used to be called MCG, Medical College of Georgia. They have a thing over there called the positron emission tomography scanning machine, and they use fluorine-18. What we do as nuclear engineers, we push things off the line of stability, and when they come back, we utilize the energy they give off. So we either find something that's naturally off the line of stability, or we push something off, and when it comes back on, we utilize that energy. That's what we do as nuclear engineers. So we utilize this phenomena of the line of stability. So what we're going to do is your teams are going to go out, we're going to all go to the lobby, and we're going to determine what the uses are of your isotope. Let's all go out here. Okay, we're going to all gather up here, and we're going to split up into teams.
All right, so bring one group over by you.
So the hydrogen team come over here, carbon team over here. Who's got the oxygen?
Right here.
Oxygen team right here, and you guys have boron.
And you stay right where you are.
All right, so we're gonna break up into teams, and we're gonna rotate. So I'm managing this team. Now what happens is, remember I said these are protons. You can see that there. These are neutrons. And so when we put them on the table can sense what isotope you're making. There's one of the sensors in the middle I think is going out, so try to stay near the edge when you do it. How many protons do you have and how many neutrons do you have?
You have 1 proton.
So go ahead and grab them down from below. And set them on the table. Just set them on the table. I think there's a bad sensor in the middle, so use the edges. They can just be anywhere. And then you hit the go button. Ready. Are you ready? Does everyone agree that's the right number? Yes. Everyone agree?
Good job. Hydrogen, also known as tritium, is a radioactive form of hydrogen.
And I work at Savannah Riverside in the tritium facilities. We make tritium, and that's what we do. We try to use that. So let's see what it's for. Push the button again.
Tritium is very rare in nature. However, tritium can be produced in nuclear reactors. Tritium is used for self-powered lighting and is used in watches, exit signs, and airport runway lights. Tritium is used in fusion reactors to produce
they use it.
energy.
You have a
and is
glow-in-the-dark
used as a
watch.
tracer
They
material
use
in
tritium. The exit signs, and when the power goes out, you want the exit sign to still glow. It uses tritium.
Tritium decays to helium-3 in about 12
It actually, they use it in airport runway lights. So if the power went out, you could still land. It's actually a very useful material. So very good. And then there are lots of other materials.
60 helps to preserve.
This only goes to
poultry,
43,
fruit,
so
and
there are other things that we use to
37
help
helps
protect
scientists improve
agriculture.
important crops like rice.
So you,
And it
all the
harmful
things that we
insect
utilize
pests
off the
without
line of
using
stability.
insecticides. And 137
Like,
also
why is it-
helps
why
ensure
is
that
it
food
so
and right level.
Because
Two helps
the
make sure wells
all of these,
are
you
strong.
can't have,
And promethium
26
147,
neutrons by itself.
thallium
It has, they won't
204,
stay together.
and krypton
So there has to be a
85 are
balance.
all used to
So when you
measure
build
the
a
thickness of
matrix, it
metal,
has all
rubber,
this other
fabric,
space. They
and
don't.
paper.
The reality is most of these aren't any color at all. They're just white. So,
You say those die off anyway?
huh?
Didn't you say they die off anyway?
It would less than a second. Yep, disappear.
Californium 252 content for road and building construction.
So we have
Radium
all of these
226
elements,
helps make
isotopes.
lightning rods work better.
And we actually make them. That's what
Gold
nuclear engineers do.
198, Iridium 192, and silver
You hit the button
110.
again.
Congratulations on creating
Good job. Ready to rotate?
Yeah, you're the one that calls the rotation.
Okay, I'm ready. I'm ready.
All right, ladies and gentlemen, we're going to rotate. So,
Thank you, guys. Go to it. He's going to tell you. He's going to. You're probably going there to rotate. You guys are going to rotate to the next team. So hold on. Wait till he goes. He's going to tell you which way to go. Come on, everyone. All right, we're here at the Interactive Nucleus. Now what happens is, remember I said that the protons are red. See the color there? The neutrons are blue. And so what do you have?
We have carbon, which is blue.
No, it's not. What happens is, how many protons does it have?
6.
How many neutrons does it have?
28.
No.
6 minus 6. And 2 minus 6 is 8.
That's right. So you have to get 6 reds and 8 blues and set them on the table. There's one of the sensors in the middle may not be working, so don't put them in these middle ones, but put them in. This thing can sense what you put down, and then it'll tell you what you've made.
Okay.
So just don't put them in these middle ones. So we have 6 red. Go ahead and put them in anywhere, except no, don't put them in the middle because I think the sensor's bad. Put them down along over here. 6 red, and you need 8 blue.
8 blue?
Right?
4, sorry.
No? Yep, put them anywhere. That's it. How many is that?
That's 8.
Are you everybody happy? 6 and 8?
Yeah.
Hit the go.
Good job. You've made carbon 14.
So you did it. So
Carbon 14 is a radioactive form of carbon that emits a beta particle.
see, well, it's blue. It's radioactive, and it emits a beta particle and becomes stable. So hit the, and we'll see the uses.
Carbon 14 is a rare form of naturally occurring
take a towel,
radioactive
like-
carbon. It's created by the sun's rays in the Earth's atmosphere. Carbon 14 is used to determine the age of organic materials up to 60,000 years old. It's also used in medical research.
So what happens is, this is archaeological. They use it to find out, because there's already carbon in the air, carbon 14. Most carbon is carbon 12, but when you breathe it in, it makes part of your body. And when you die or an animal dies, it stops. You stop breathing it in. So however much you have, and then it turns into nitrogen. So
Tracer because it's got such a like a slow radioactive life.
that's right.
They use it to detect cancers in your blood.
They can do a lot of things with it. That's right. So very good.
Many radioactive materials are used in medicine.
There's some medicine ones. This only goes up to potassium. So there's some other ones we use like technetium 99. They actually, you use it to tell if you have heart issues and things like that.
Come out of your body so a special camera can determine the health of your bones. Thallium-201 is another important radioactive material
So they
used
just,
in medical imaging.
this one, heart disease.
Thallium-201
as
provides
well.
X-ray radiation that will come out of your body so a special camera can determine the health of your part. Iodine-131 can be used in medical imaging.
This is a
and
therroid.
treat thyroid cancer.
So they can use it to image
Iodine-131
your
emits
thyroid.
beta particles and
So that way
provides gamma rays.
it's X-ray, but the gamma rays are coming out of your body instead of coming through your body.
The beta particles and gamma rays can be used to treat thyroid cancer.
What can be?
Gamma rays.
No, not necessarily. Not necessarily. So very good. Ready to rotate. Thank you. What tile do you have? 5 boron 10. So how many protons do you have? Now, protons are red. You can see the color here. Neutrons are blue. So you reach down and you have, how many protons do you have? 5. How many neutrons? 5. So put them on here. I think one of the middle sensors may not be working, so put them anywhere except right in the middle.
Okay, 1. I just put them all around.
Yep, put them in.
2. Oh yeah.
That's all right. That's all right. We'll try it.
4.
Put in there. Now 5 blue ones too, right? Okay. Hit the go button. See if you did it.
Congratulations.
Boron
You
10.
made boron 10.
Very good.
Boron 10 is a stable form of
It's a stable form of boron. It's got a good balance with the 5 and 5, right? Hit it again.
boron. It is a hard, black
That's what it really looks like.
with a high melting point. It is an essential nutrient in plants.
So it's in plants.
Boron 10
We also use it in nuclear reactors, and it's used in
nuclear
medicine.
reactors and in medicine to treat tumors.
So that's what boron 10 is used for.
Other nuclear materials
And then we
are
use it
used
in
to create
electrical
electricity.
generation, some other materials.
Nuclear fuels heat water to create steam.
If you guys come back here on your own time, you can, this is here all the time, you can play with it. And you can look at these slides where this is how a nuclear reactor works.
Nuclear power comes from the energy that is released when an atom's nucleus fissions or splits apart.
That's my voice.
Fission occurs after a neutron is
My voice
absorbed
isn't
into
as
a
good as Morgan
fissionable
Freeman's?
nucleus. In order to control the nuclear chain reaction, some of the neutrons need
So
to
you
be
have lots of
absorbed.
these are other elements, cobalt, hafnium, gadolinium, samarium. There are other things we use.
On creating an
Good job.
atomic nucleus.
I'll try to be more like Morgan Freeman.
What would you do with the atom you created?
All right, thank you. Rotate when you're ready. Gary, we're ready to rotate. All right, next one.
Pour on our control rods.
We actually dissolve it into the water, and it actually goes around as part of the water. It's
Oh, it's part of the cooling.
that's,
Interesting.
Some balls on the table.
yeah, you did. All right,
You haven't created anything.
all right, hold on. All right, so you have 8 oxygen 16. So how many protons do you have? Protons are red. There's the neutrons are blue. So 8 protons. How many neutrons? 8. So and this is stable, right? Because of green. So it should, because it's a good balance. So go ahead and grab them down from the hopper down below. Some of these one of these middle sensors we think is not working. So don't put them in the middle group, but just anywhere around. Just set them in here. It'll.
We got 8, right?
8 and 8.
Cool ping pong balls.
All right, so are you ready? You got 8 and 8? Looks like it. Go ahead and hit the go button.
Congratulations, you made oxygen 16.
You did, oxygen 16, huh? There's little light sensors in there that can determine it. That's where one of the sensors is bad. So hit it again. Let's see what oxygen 16 is used for.
Oxygen is the
the most abundant
Colorless, tasteless gas that is
isotope on Earth. It's what you breathe.
used in life support in aircraft, submarines, space flight, diving, medicine, rocket propulsion, the production of steel.
So you can see it's used in almost everything. So it's really important. And so,
Oxygen is needed for combustion.
you know, as you go through this line of stability, you can see other people had different ones that are used for different functions. So they're interesting. Some radioactive and some stable. So good job. There are some other isotopes that are used. We have remote power uses.
Places.
Now this only goes up to 43, so the bigger masses. Plutonium 238 we make at Savannah River site.
For deep space satellites.
That's how it powers all the satellites that we send out to deep space. They have to use plutonium in a reactor.
Plutonium 238.
They actually used it as to power for your heart. For people who, they used to in the 70s, they had plutonium in your heart to keep your heart pumping. Now they use other types of batteries. But originally they did that.
Polonium 210 can also be used in remote power
Polonium 210, same thing.
Congratulations
Good
on
job.
creating. What would you do with the atom you created?
Okay, Gary, I think we're ready to go back to the room. Good job, guys. We'll all go back to the room. You should have 4. Perfect. Four. Got it.
Pink cards and pencil, if you've got one of those, if you could return it to me.
All right, everyone, and go ahead and take your seats. How much time we have left, Gary?
About 10 minutes.
10 minutes. I'm going to show you, we're going to go over the last few things. That was good.
Right down to there, and I'll be right in the same spot.
Okay, so we built our 3D periodic table. Now this was the chart of nuclides. If you recall, let me turn my laser back on. If it was up in, this is the number of protons and this is the number of neutrons and this is the whole thing. Someone asked me out there why the chart we have on the interactive nucleus that shows all of these space out here is red. Reality, it's just these ones here. So it just follows. You can see the black here is stable. The multicolored ones are the radioactive ones, and the red ones are the unstable ones. And so they exist only because we created them to see if they exist physically. This is a blow-up of the area, expanded view of the area above lead. It has uranium and plutonium, americium, curium. And so this is what we work with in nuclear power. The thorium-232 occurs in nature, uranium-235 and uranium-238 occur in nature, and that's what powers nuclear reactors. So the chart of nuclides, the whole point of today was for you to see that line of stability and understand what nuclear engineers do. We push things off of it, and as it comes back on, we utilize that energy, or we find something that's naturally off of it, that, like uranium is naturally off the line of stability, trying to get on the line of stability, and we use that energy. Any questions on that? Did it make sense? All right, so I'm going to show you some of the uses of some of the isotopes. Some of you got this from the chart from the interactive nucleus that we played out in the lobby. We use nuclear technology to determine how much Coke is in a bottle of Coke, how much 7-Up's in a bottle of 7. You ever been to the world of Coke and seen the Coke bottles going by fast? They can't measure it by weight very easily, but they can use radiation sensors to tell when it gets to a certain point and it stops. We can determine how much explosives or drugs or weapons, if someone has it on an airplane, to prevent that from happening. Insulation on wires, sources of pollution, small leaks. We can define those leaks using radioactivity, termite damage, age of formally living things. Whoever had carbon-14, that's how we use it for. Power for space exploration. Some of us talked about that at the interactive nucleus. We use it in agriculture to help improve the nutritional value of agricultural products. We use it in, we irradiate foods if we irradiated all of our ground beef and hot dogs and things, we would eliminate food salmonella. If we did it for chicken, it would kill that bacteria, but not change the meat. But it's a little bit more expensive than how we do our foods now, so we don't do that. But it would eliminate all of those diseases. Energy production, we use it to produce power in nuclear power plants. There's no burning. Over 50% of South Carolina's energy is from nuclear power. If you have an electric car in, not a guitar, a car, if you have an electric car in South Carolina, you have a nuclear powered car, because over 50% of the power in South Carolina is powered by nuclear power. We use it in consumer products. Smoke detectors have americium-241 in it. Watches, clocks, and exit signs have tritium in it. So if the power goes out, they still light up and you can escape. Your computer disks are used radiation to make them not have no static. Nonstick pans, same way. Photocopiers, same way. Cosmetics, contact lens solutions, they are sterilized using radiation, so it protects you from getting bacteria in your eye. We use it in medicine. Over 1/3 of all hospital procedures use nuclear medicine, where we use nuclear technology. Now this one, who here would drink a concentrated drink of radioactive fluid? Who would drink if I gave it to you, would you drink a concentrated drink of nuclear fluid, radioactive fluid? Sure, Georgia hat, I guess. The reality, most people will, because this is a bone scan. The person drinks a radioactive fluid, the radioactive material goes to their bones, the radiation comes out, and there's a sensor like this that scans them, and then their body flushes all the radioactive material away and it's gone. And they can find really detailed injuries to your bones. Before, they would have to cut you open to look, and it would take weeks to heal. And so this other thing just goes through you and it just takes a picture. Which would you take? Would you rather have surgery or take the drink? You changed your mind a little bit, right? So it's a much better method than a surgical procedure. We use it in industrial applications. We check our welds in our cars. We check welds in airplanes to make sure they're made soundly so they'll fly well. We use it in identifying where oil is that we can find. How thick a can is, like your Coke can, how thick that aluminum is. They use radioactivity for that. How thick your paper is. When they make sandpaper, they use it 3 times. How thick the paper is, how thick the glue on the paper is, and how thick the sand on it is. And construction as well. And that's all we have. Any questions? Questions about nuclear? Questions about isotopes? Any questions? Anybody? That's the whole presentation. Yes?
When you have a cancer patient, they go in for chemo radiation. How, if the radiation is supposed to be beneficial and the therapy is supposed to be beneficial, then why can side effects lead to hair loss and other things?
Well, chemotherapy is not using radiation; it's using chemicals. But radiation, what happens is radiation or chemicals, and for chemotherapy, they try to damage the cells that have the cancer. But it's very difficult to target that. It's one specific cell. And so especially if it's widespread in your body. So there's collateral damage that happens. It damages some other things. And hair, anything that's fast growing typically gets damaged more easily. So things like hair, but it grows back. So it's a short-term thing. So. That's right. That's exactly right. But you'll see there's a machine over at Georgia Regents University called the gamma knife, and they have a whole bunch of small gamma radiation sources, and as they go through, they're not very harmful, but they have a whole bunch of them as they crisscross. It makes a high gamma at that one spot, so they can actually target very specific spots and not hurt the rest of your body. So they can use radiation in different ways. So that's a good question. Yes. It's probably an MRI, is that what we're talking about, or a CT scanner? There's different kinds of scanners, but I'm not a doctor, I'm a nuclear engineer, so I don't understand those machines very well, but I know they're doing some things this week over in Georgia, so I don't know if I think you're probably in school during the time, but it's really interesting technology, and it's really helpful, very helpful. Any other questions? Well, thank you for participating. You guys really did well today, and when you go to the next class, you're going to learn about electrons, and they're important because all chemistry is electrons, but they're driven by the nuclear part. So, thank you. Bye, everybody.